Since the earliest days of statistical mechanics, thermodynamic entropy has frequently been understood as a measure of our ignorance of the exact microstate of a macroscopically large system. The similarity of the mathematical expressions for the Gibbs entropy and the Shannon information measure have lent support to this view, to the point where physicists such as Ed James argued that entropy should be understood entirely in information theoretic terms. However, simply having the same mathematical form should not be enough for this identification to be made. It must also be the case that a change in information should be accompanied by an equivalent change in entropy.
Landauer's principle seems to supply just the needed ingredient. It relates the change in the abstract information from a computation to a minimum thermodynamic cost in the form of heat generated in the environment. This minimum is defined purely in terms of the information processing operation itself, and so every physical system which performs the computation must pay at least this cost. The cost is exactly the change in Shannon information over the computation multiplied by the temperature of the environment, and is what we would be expected if information and entropy were the same. The development of quantum information and quantum computing changes our notions of information and its relationship with entropy. In quantum information processing, logical states are replaced by quantum signal states, and logical operations are replaced by quantum operations. A quantum operation is any allowed transformation that can be performed on a quantum state using the usual rules of quantum state development. This can involve auxiliary systems, which are used to catalyze the operation by interacting with the signal states.
At first sight, the generalization of Landauer's principle to quantum information processing seems straightforward. The Gibbs entropy is replaced by the von Neumann entropy, and Shannon information is replaced by Schumacher information, maintaining the equivalence of the mathematical forms of information and entropy. It is relatively straightforward to derive an inequality which says the heat generated by a quantum operation is at least the change in the Schumacher information over the operation multiplied by the temperature. However, an important part of the classical Landauer's principle is that the relationship is a tight band. While there are practical barriers to reaching the limit, such as finite size effects, time, etc., there is no physical principle that prevents these barriers becoming arbitrarily small, and experimental tests are increasingly pushing at this boundary. It is only by approaching this limit that computations can become thermodynamically reversible.
In our paper, we show that quantum computers cannot, in general, reach the limit for heat generation given by the Schumacher information measure. This means that there is a necessary excess heat dissipation that is specific to quantum computation. Even in the limit of idealized heat baths, work reservoirs, and long times, the information theoretic cost given by the change in Schumacher information is not physically possible. Quantum computing carries a fundamental excess thermodynamic cost that makes it inherently thermodynamically irreversible, and the tight connection between information and entropy is lost.